If AI4 is already, like Elon Musk says, good enough to deliver self-driving that is several times safer than a human, then why is Tesla in such a hurry to build AI5 and even planning AI6, AI7, and AI8 already? There is really only one reasonable explanation. Tesla's endgame is not about selling cars at all. Right now, Tesla is going through a complete transformation. On one hand, Musk is talking about building a terafab that can produce 1 million wafers a month. That would put it almost on the same scale as TSMC. On the other hand, he is putting Dojo 3 and space-based compute on the table. This tells us that in the future, Tesla's core product might not just be cars. It might also be AI compute. That may sound a bit far off, but if we break down Tesla's technical roadmap, you will see it is actually a very tight loop. Compute, energy, manufacturing. Today, we are going to run some numbers. Where does Tesla's 100 billion chips a year demand actually come from? Does moving data centers into space make sense in terms of physics and energy cost? And where does this whole chain of moves actually take Tesla in the end? Let's start with a picture of the future. One day, the cars on the street are no longer regular taxis. They are a massive fleet of fully autonomous robotaxis. In factories and office buildings, there are tens of thousands of Optimus humanoid robots. They move goods, tighten screws, clean floors, and even serve coffee. Every car, every robot, is actually a mobile AI compute node. Right now, each Tesla already carries a chip that is close to a small data center in capability. What about future Optimus robots? Musk's own estimate is that Optimus demand could eventually reach 10 to 20 billion units. Even if we do not look that far, just look at the first few years, a few million robots per year. Each robot has to handle 3D, space, vision, touch, motion control, and language understanding at the same time. The compute density it needs could be 5 to 10 times that of a car. On top of that, you have cloud compute and future space-based training clusters. To train trillion or even tens of trillions parameter multimodal models, Tesla needs to build exascale and even zettascale supercomputers. Quick refresher. Exascale is exaflop. That is 10 to the 18 floating point operations per second. Zettascale is zettaflop. Another 1,000 times higher. The world's fastest supercomputers are only just touching the exascale threshold. Tesla wants to turn that level of compute into its own basic infrastructure. And it is not just about buying some GPUs. You also need a full stack of networking chips, power management chips, memory interface chips, and more. This is the reality Tesla is facing. A growing compute black hole. So here is the question. Can you just keep stacking compute forever? At what point do you hit a wall? This is where two concepts come in. The compute wall and the energy wall. The compute wall is easy to understand. NVIDIA's GPUs are powerful, but production capacity is limited. The more advanced the process node, the slower the ramp, the more insane the price. Traditional foundry expansion runs on an 18 to 24-month decision cycle. AI compute demand is growing exponentially. If you rely entirely on buying NVIDIA, you will eventually find that it is not that you do not want to buy, it is that you cannot buy, or that NVIDIA simply cannot produce enough. The energy wall is even harsher. Next to Giga Texas, Tesla is building the Cortex cluster. The plan is to have more than 100,000 H100 and H200 class GPUs. Public information says that when this cluster starts in 2024, it will need about 130 megawatts of power. 18 months later, that could jump to over 500 megawatts. What does 500 megawatts mean? Roughly the full output of a small nuclear power plant, or a large gas power plant. All of that electricity eventually turns into heat. Then you have to spend huge amounts of water, air conditioning, and cooling towers to get that heat out. Even if you push PUE to 1.2 to 1.5, the operating cost is astronomical. PUE, or power usage effectiveness, is a key metric for data center energy efficiency. So you can see a very clear logic. Terafab is meant to solve the compute wall. Dojo 3 and space-based compute are then used to push through the energy wall. Let's talk about Terafab first. In November 2025, at Tesla's shareholder meeting and the Barron Investment Conference, Musk dropped an industry bomb. He said Tesla will need 100 to 200 billion chips per year in the future. In the context of traditional car makers, that number is pure science fiction. It exposes a simple fact. Tesla no longer sees itself as a car company, it sees itself as a large-scale AI, robotics, and inference compute company. To match that demand, he gave it a name, Terafab. Tera means trillion. Musk's target for Terafab is an initial capacity of 100,000 wafers per month. Long-term, he wants to push that to 1 million wafers per month. For comparison, TSMC's total capacity across all nodes is about 1.4 to 1.5 million 12-inch wafer equivalents per month. Samsung's foundry capacity is about 1/3 to 1/2 of TSMC's. If Tesla really pushes Terafab to 1 million wafers per month, then a single company would instantly become one of the top 2 wafer manufacturing forces in the world. In some nodes, it could even arm wrestle with TSMC. The problem is, how much money does that burn? A 3nm or 2nm fab with 100,000 wafers per month costs about $25 to $30 billion to build today. 1 million wafers means 10 such fabs. Total investment north of $250 billion. You can think of it as building several more Shanghai gigafactories. But the difficulty and precision are on a completely different level. A car plant is steel, concrete, and robots. A wafer fab is precision engineering, where every speck of dust can be fatal. Even with Tesla's strong cash flow, carrying $250 billion of capex alone would be suffocating. That leads to a key idea. Many analysts believe Terafab is unlikely to mean Tesla builds 10 fabs itself. It is more likely a Virtual IDM model. A Virtual IDM means Tesla does not necessarily own the buildings and land. Instead, it can sign deals with an existing chip manufacturer. For example, Intel. Tesla pays to lock up most of the capacity of a new fab. It can even participate in equipment selection and process customization. That production line effectively becomes a Tesla-dedicated line. Front-end wafer processing could run on Intel 18A or even more advanced nodes. Back-end packaging would use Intel's specialty, EMIB, the Embedded Multi-Die Interconnect Bridge. The advantage of EMIB is that you do not need a huge silicon interposer. You can tile multiple dies together like a puzzle into one giant system. You are not limited by reticle size. It is perfect for monsters like Dojo that integrate at wafer scale. For Tesla, this has several benefits. First, it does not have to learn how to run a fab from scratch. That avoids a huge amount of trial and error cost. Second, it still gets near in-house levels of control and priority. Third, from a geopolitical angle, Intel expanding in the US can get government subsidies and avoids Taiwan Strait risk. For Intel, Tesla is a lifeline. Intel's IDM2 strategy needs big external customers to fill 18A capacity and prove it can compete with TSMC. A customer that says, "I want 100 billion chips a year" is basically a gift from heaven. Of course, Musk is not going to play by all the traditional rules. When he talked about building fabs, he threw out a very controversial idea. Are modern fabs over-obsessed with clean room standards? He has publicly said he wants to smoke cigars and eat burgers inside a fab. Then he questioned, if wafers spend most of their time inside sealed pods and tool chambers, why does the entire building need to be Class 1 clean? Can we make only the tool interiors and transfer paths ultra clean? Then relax the cleanliness of the general factory environment. That way, construction cost and operating energy use could drop a lot. From a first principles perspective, it sounds somewhat reasonable. Wafers travel in FOUPs. They are processed in vacuum chambers. In theory, as long as the interfaces are sealed, dirtier outside air should not matter much. The problem is, semiconductor experts are almost unanimously saying, do not mess with this. At 2 nanometers, sensitivity to particles is extreme. A few nanometers of dust can kill a transistor. The hydrocarbons and metal ions in cigar smoke, once they get into photoresist, yield collapses. So a realistic view is, a completely dirty fab is impossible. But Tesla might try a hybrid cleanliness factory architecture. For example, only the most expensive EUV lithography area keeps extreme cleanliness. Other areas lower the standard. Highly automated sealed transfer systems keep the risk within a controllable range. This is classic Musk style. Use first principles to challenge industry consensus. Sometimes he really does reinvent an industry. Sometimes he dances on the edge of disaster. So who is this massive terafab plan meant to feed? The answer is Tesla's own AI chip roadmap. Ai4, Ai5, Ai6, Ai7, and later Ai8 and Ai9. Let's roll the timeline back to Ai4. That is what most people know as HW4. Ai4 is built on TSMC's 4nm and 5nm processes. Compared with HW3, performance is about 3 to 5 times higher. Camera resolution is pushed to 5 megapixels. The ISP is stronger. It is the main chip in current production cars. Musk positions it as the foundation for achieving FSD that is safer than humans. But Ai4 has already been written into the transition chapter. As FSD algorithms move fully to end world models, model parameter counts explode. Video resolution and frame rate go up. AI4 starts to hit limits in memory bandwidth and energy efficiency. It is more like a stepping stone that helps Tesla cross the human safety baseline. It is not the endpoint. The real watershed is AI5, if we use a simple analogy. AI4 is a high-end gaming PC. AI5 is like putting a near data center class AI card into the car. Industry chatter and supply chain leaks all point to a range. AI5's compute target is 2,000 to 2,500 tops. That is about 5 times AI4. Memory capacity goes up 9 times. Raw compute goes up 8 times. The more shocking part is energy efficiency. Musk has said publicly that a single AI5 can approach the performance of an NVIDIA H100. 2 AI5 chips together can approach a Blackwell B200. But the power target is only 150 to 250 watts. An H100 is a 700-watt class monster. You can sum it up in one line: take a data center class chip, then compress it down to the power budget of a laptop power adapter. How critical is that for robotaxis? Cars run on batteries. Every extra kilowatt hour the chip consumes is 1 less kilowatt hour for driving. If you want robotaxis to run around the clock and still make money, the chip has to be both powerful and extremely efficient. Otherwise, all your compute advantage turns into electricity bills and range anxiety. AI5 is expected to start trial production in the second half of 2026, mass production in 2027. To hit that schedule, Tesla is taking a very aggressive manufacturing strategy: dual foundries. On one side is old friend TSMC. It will use N3P or N3E, the most mature 3nm processes, to make the first high-performance versions. That ensures stability and yield. On the other side is Samsung. At its new fab in Taylor, Texas, it will use a 2nm GAA process for another portion of the chips. Tesla is betting on longer-term energy efficiency and performance potential. This is a bit like the iPhone 6S era A9 chip. The TSMC version and the Samsung version had different battery life. That triggered Chipgate. Now Tesla is basically recreating a Chipgate 2. Different foundries and different transistor structures mean different physical characteristics. Musk can say software will ensure a consistent experience. But from an engineering perspective, Tesla will likely do a few things. First, bin the best chips and put them into high-end models or heavier workloads. Second, use average chips in regular cars or run them at slightly lower frequency. Third, use firmware-level frequency and power management to minimize differences that users can feel. At the same time, AI5 has to clear a higher safety bar. ASIL D. Robotaxi fault tolerance cannot be compromised. AI5 must meet ASIL D, the highest automotive safety integrity level in ISO 26262. That means the allowed failure probability is so low it is almost negligible. Current HW3 and HW4 already use a dual-sock redundant architecture. AI5 will continue and even strengthen this. 2 AI5 chips in the car receive sensor data at the same time. They run inference in parallel. A separate safety island monitors them. Once it detects abnormal output from the main chip, the backup chip must take over within milliseconds. You can think of it like a plane with 2 engines. If one fails, the other must keep the plane flying until it lands safely. AI5 will also integrate some lockstep cores. These do not run big models. They run traditional safety monitoring code. Their only job is to watch the main system and stop it from going crazy. After AI5 comes AI6. The most dramatic thing about AI6 is not how much faster it is than AI5. It is its identity. At first, Tesla thought training and inference were 2 completely different workloads, so it built D1 as a dedicated training chip, then it built Dojo 1 and Dojo 2. But with the rise of end-to-end large models, the compute patterns of training and inference are getting more and more similar. Both are dominated by large-scale matrix operations. If you maintain 2 completely different hardware and software stacks, one for cars, one for data centers, your R&D cost, mass cost, and software maintenance all double. So in 2025, Tesla did something pretty bold. It killed Dojo 2 and pivoted to a unified architecture. Musk said AI6 will be used in Optimus and in data centers. Dojo 3 can be understood as a board that integrates a large number of AI6 SoCs. In other words, AI6 is no longer just the next car chip. It is the general purpose core for cars, robots, and data centers. In cars and robots, it is a low-power inference chip. In the data center, thousands of AI6 chips are tiled together like Lego bricks. That becomes the heart of the new Dojo 3 training system. Technically, AI6 will likely use more aggressive 5D and 3D packaging, for example, TSMC, CoWoS, or Samsung iCube. It will hang HBM4 high bandwidth memory around it to break the memory wall in large model training. Chip-to-chip interconnect will be greatly strengthened. Each AI6 will be able to talk at high speed across boards, racks, and even between data centers. The benefits of a unified architecture are very direct. Mask and NRE costs can be amortized over tens of millions of units. Per chip cost drops sharply. The software team only has to maintain one backend. All use cases benefit together. For NVIDIA, this is painful. NVIDIA has to serve all industries with general-purpose GPUs. Tesla only serves its own driving and robotics workloads. It can use a specialized architecture that is cheaper, more efficient, and better tuned. That is enough to create an advantage. Further down the line is Ai7. Ai7 has a very special mission. Musk has already made that clear. It is the first AI chip designed for space environments. It is the core of the space version of Dojo 3. It is the heart of space-based AI compute. How harsh is space on chips? Put simply, a normal 3nm or 2nm chip in orbit might start throwing errors within hours. It might even die outright. High-energy particles hit transistors and cause single-event upsets. Bits flip randomly. Temperature swings are huge. One side faces the sun, the other faces deep space. The difference can be tens or even over 100 degrees Celsius. In vacuum, there is no air to carry heat away. Fans are useless. You can only rely on thermal radiation. So Ai7 has to solve more than just compute. It has to handle radiation, heat dissipation, and reliability. At the design stage, you need radiation-hardened cell libraries. You need triple modular redundancy. 3 cores compute the same thing. A voter circuit cancels out single-point errors. You need shielding with water, polyethylene, or even Starship stainless steel hull. You need to rebalance power and cooling so the chip does not cook itself in vacuum. From a capability perspective, Ai7 marks Tesla's move from consumer electronics-grade chip design into space-grade electronics. At this point, you might wonder, with so many chip generations, will this take forever to actually produce? NVIDIA's cadence is already considered fast. It still takes 18 to 24 months per generation. Yet Musk says Ai7, Ai8, Ai9 will come every 9 months. How is that possible? This is Tesla's accelerated attack on Moore's law. Traditional semiconductor cadence is 18 to 24 months per architecture generation. Transistor density doubles. Tesla is now saying Ai7, Ai8, Ai9 will follow a 9-month cadence. Others update every 2 years. Tesla updates 3 times in 1 year. It sounds like bragging, but there is a method behind it. First, pipeline-style parallel development teams. Imagine 3 teams running at the same time. The alpha team is doing physical design for Ai7. The beta team has already defined the architecture for Ai8. The gamma team is exploring what operators and memory topology Ai9 will need based on the latest algorithm trends. If one generation gets stuck, the next 2 do not completely stop. Second, AI-enhanced EDA tools. Chip design has a lot of grunt work, layout and routing, signal integrity analysis, automatic test generation. In the past, humans plus scripts might take months. Now machine learning models can predict and optimize. Verification cycles can be compressed to weeks. Third, chiplet modularization. Tesla will not redesign a giant monolithic chip from scratch every time. It will break the chip into multiple chiplets. I/O, memory controllers, SRAM, and other mature blocks are reused as much as possible. Every 9 months, only the critical NPU compute tile is updated. It is like building with blocks. You only swap out the central compute engine each time. Risk and time stay manageable. Let's do a simple compounding comparison. Suppose NVIDIA updates every 18 months. Each time, performance improves 2 to 3 times. That is 2 generations in 3 years. Tesla updates every 9 months. Even if each generation only improves 1.5 to 2 times, that is 4 generations in 3 years. Stacked together, in Tesla's own vertical workloads, it can create a, by the time you catch up, I have already updated again advantage. The key point here, Tesla does not need to crush NVIDIA in general purpose compute. It only needs to be cheaper, more efficient, and better tuned in its own core workloads, autonomous driving and robotics. That is enough. Now that we have covered chips and fabs, let's go back to the crazy question from the beginning. Why move data centers into space? We already said, ground-based data centers are hitting the energy wall. Cortex at 500 megawatts is like a small nuclear plant. The grid has to be upgraded for you. Cooling needs millions of tons of water. Even with optimized PUE, the cost and environmental pressure are huge, Musk said at Davos. The most expensive things on Earth are not chips. They are clean power and cooling capacity. The ultimate solution is to move data centers into space. Space has two natural advantages. First, energy. The solar constant is about 1,360 watts per square meter. There is no atmosphere and no clouds. Solar panels can generate several times more effective power than on the ground. In sun, synchronous, or other special orbits, there is almost no night. Solar panels can see sunlight almost 24 hours a day. You do not need massive battery storage. Musk estimates that in space, per unit area solar power generation could be more than 5 times that on Earth. Second, cooling. Deep space has a background temperature near 3 Kelvin. That is close to absolute zero. As long as you have large enough radiators, and you keep them facing away from the sun and toward deep space, you can dump heat through radiation. In theory, you can get PUE very close to 1. Almost no air conditioning. Of course, this is not a sci-fi movie. It is a hardcore engineering problem. In vacuum, there is no air convection. Fans do nothing. Cooling is governed by the Stefan Boltzmann law of thermal radiation. You need huge radiator wings. Once deployed, they look like giant wings. SpaceX and Tesla's idea is to use Starship's lift capacity, launch full racks of servers, radiators, and power modules into orbit in one go, then deploy the radiators. They always keep their backs to the sun and face deep space. We already talked about radiation. Ai7 has to handle that at the architecture level. Outside, you still need shielding with water, polyethylene, and stainless steel. Single event upsets need triple modular redundancy and error correcting codes as backup. There is another key prerequisite: launch cost. If launch still costs thousands of dollars per kilogram, sending tons of silicon and radiators up is far more expensive than building a few more power plants on Earth. Only when Starship truly achieves full reuse and pushes launch costs down to tens or around $100 per kilogram, will the total cost of a space data center possibly drop below that of a ground one. Data links are also a real issue. Training large models needs massive data. You cannot send all of Earth's video and sensor data up to orbit and back. Bandwidth and latency would kill you. So, a more realistic path is this. Space Dojo mainly processes native space data, satellite imagery, astronomy observations, Starlink network data, or it generates synthetic data and does model fine-tuning. It will not move all training into orbit. Underneath all of this is the basic infrastructure: Starship and Starlink. Starship's low Earth orbit payload is 100 to 150 tons. The target launch cost is $100 per kilogram or even less. Only when that number is real does launching a full space data center become economical. Starlink V3 satellites have laser inter-satellite links. They can form a terabit per second class backbone in space. Space data centers can interconnect with each other. They can also sync model parameters with ground stations at high speed. You can think of it as a fiber backplane wrapped around the Earth. Some companies are already testing this. For example, a startup like StarCloud has reportedly launched test satellites carrying NVIDIA H100s. In the future, they might use Tesla's Ai7, or they might simply be absorbed into Tesla's ecosystem. Now let's pull the camera back to Earth and look at Tesla's current compute layout. It runs on a dual-track system. One track is the reality line of defense, Cortex, a supercluster based on NVIDIA H100 and H200 on the order of 100,000 GPUs. It is the main training workhorse for FSD and Optimus today. It solves the right now problem. FSD V13 and V14 need constant iteration. Robots need to go to work. You cannot wait for in-house chips to mature. This setup alone creates a very high industry barrier. 100,000 H, 100S plus power, cooling, and buildings is a multi-billion-dollar investment. Most car makers cannot play at this level. The other track is the future chip, Dojo 3, built on the unified Ai6 and Ai7 architecture. Musk no longer pitches Dojo as something that will immediately kill NVIDIA. He frames it as a long-term strategic chip. It has 3 layers of meaning. First, cost. Once Ai6 and Ai7 mature, Tesla can expand compute at a lower cost per TOPS. It will no longer be fully at the mercy of NVIDIA's pricing. Second, bargaining power. As long as Dojo exists, NVIDIA cannot freely raise prices or cut supply. Dojo is Tesla's nuclear deterrent. Third, security. If GPU export controls tighten in the future, Or if some geopolitical event breaks the supply chain, then Dojo and Ai6 chips manufactured by Samsung and packaged by Intel become Tesla's compute lifeline. Speaking of supply chains, we have to talk about a three-kingdom story in semiconductors: TSMC, Samsung, and Intel. Their roles are being reshuffled. In recent years, Tesla has had to rely almost entirely on TSMC for advanced nodes. TSMC's N3P is currently the most mature and highest performance 3nm process. Giving the first Ai5 orders to TSMC is about having a stable and reliable hardware base when robotaxis go live. But you can see TSMC shifting from the only leading man to the main leading man. Tesla is clearly reducing single supplier dependence. Samsung is moving from backup to one of the main players. It has big Ai5 and Ai6 orders. It is betting heavily on 2nm GAA. Samsung's SF2 process uses a gate all-around structure. In theory, at the same power, it can run at higher frequency. Or at the same frequency, it can be more efficient. The problem is, yield ramp at 2nm GAA is very hard. Reports say Samsung's 2nm mass production might slip to 2027. If Samsung's yield does not improve, it will directly affect Tesla's entire product roadmap. Tesla's calculation is simple. Use huge orders to force Samsung to polish its process. Use TSMC as a safety net. It is betting that Samsung can make AA work. If that bet pays off, Tesla gets a long-term edge in energy efficiency. Intel, on the other hand, is moving from old rival to packaging ally and virtual IDM partner. Tesla likes Intel's 18A process, US-based capacity, and EMIB packaging. EMIB is not limited by reticle size. It can stitch together very large multi-die systems. That is perfect for Dojo's wafer scale style architecture. More importantly, Intel's advanced packaging facilities are mainly in the US. That fits US government sovereign compute security goals. It can also tap CHIPS Act subsidies. For Tesla, once it deeply binds a line at Intel, part of Terafab is effectively hosted inside Intel's fabs. All of this together forms the supply chain backbone of Tesla's compute energy manufacturing loop. But we should not forget, this is also a trillion-dollar scale bet. Terafab, Cortex, Dojo 3, and space data centers together mean long-term, continuous, massive capital expenditure. 10 3nm and 2nm fabs cost around $250 billion. Launching thousands of compute satellites depends on high-frequency Starship reuse. Cortex alone is a multi-billion-dollar project. Tesla's cash flow is strong, but the car market is in a price war. If Robotaxis, Optimus, and cloud compute do not commercialize as fast as expected, cash flow pressure will be intense. Technical uncertainty is also huge. A 9-month chip cadence leaves almost no room for error. If one generation fails at tape-out or has terrible yield, the whole roadmap might slip by a year. Samsung's 2nm yield, Ai7's radiation hardening, Starship's reuse progress, any one of these breaking can ripple through the whole system. Space compute maintenance is no joke either. A small micrometeorite hitting a radiator wing could destroy an entire data center. Orbital debris and space weather are real problems. So, if you want to judge whether this bet has a real chance, there are two key indicators to watch. First, the mass production yield of Ai5 and Ai6, and how they actually perform in the fleet and in robot. Does compute reach the target? Is power under control? Does safety meet the bar? Second, Starship's launch cadence. And whether we start to see missions that carry AI compute modules into orbit, do experiments like StarCloud scale up? Does Tesla itself start launching Dojo modules into space? Let's wrap up the story. What Tesla is doing now can be summed up in one sentence. It is transforming from a car company into an AI compute and energy infrastructure company. Terafab answers the question, how much compute do I have? Through a virtual IDM model, dual foundries, and EMIB packaging, Tesla is going after a slice of the pie that used to belong to TSMC, Samsung, and Intel. Space Dojo answers the question, where does this compute get its power and how does it cool? Using Starship and Starlink, Tesla wants to move data centers to a place where solar energy is effectively unlimited and the cold sink is effectively unlimited. FSD, Optimus, and future AGI are the applications that will run on top of this compute. That is the layer that makes money. Maybe 10 years from now, when we talk about Tesla, we will not call it an electric car company. We will say it is the first company that truly closed the loop between energy, compute, and manufacturing, a silicon-based civilization company. As for this giant bet, Will it become a success on the scale of Apollo that ends up in history books? Or will it be another long, drawn-out Mars colonization-style experiment? Right now, nobody knows. But one thing is certain, in the next few years, the mass production performance of Ai5 and the launch cadence of Starship will decide whether this story is written into business history as a great new paradigm, or into investor memoirs as that line. If only we had known back then.